this is it.
Progress.
Hi, Jordan.
Hello.
How you doing today?
Good. I'm tired.
You're tired. I was up until 2 o'clock doing this silly example. So this is Jordan. I know you're a good student, and I know you want to do things perfectly. Okay?
Yeah.
That's the kind of person you are. You are going to get extremely frustrated by this lab.
I did. I finished it already.
Okay. You know what I'm talking about then.
Yeah.
Okay. It's like if you miss, if the weight was from the subtraction was 21.10 and you put 21.11, it flagged you and you had to go figure out why the thing was wrong.
Yeah.
And for the longest time, I couldn't put the calorimeter on the balance because I didn't put the stir bar and the cork lid on top. So I believe it or not, I did this laboratory, did the simulation all the way through like you guys did.
Mm-hmm.
Did you get through it? The nice thing is, at least you know you got all the answers correct.
Yeah.
You got 100%?
I think I got like a 99 because I got one of the volumes wrong. I put like 47.0 and then it said it wrong.
Yeah. Yeah. The other thing was that the last step, I got what I screwed up on was the Van Hoff factor. I got the slope, but I forgot to divide the slope by the KF.
Mm-hmm.
And you have to do that in order to get the Van Hoff factor. So I had the slope in that line rather than the division.
Mm-hmm.
Gianna, how are you doing?
Pretty good.
Have you done the lab yet, Gianna?
No, I haven't done it yet. I was doing it
All right.
today.
No. Okay, just beware. It is very, very frustrating. I
Okay.
literally myself, it took me, I'm really not kidding you, 2 sessions, 4 hours to get through it. Okay,
There
so
you
just be prepared.
go. Okay.
Read the instructions that they give you. For example, they tell you to stack one cup on top of the other,
hmm
and I did that, and then I skipped to the next step, which was put the calorimeter on the balance. Okay. I didn't read the last part of the first instruction, which said put a stir bar in there and the cork lid. So I sat there for about a half an hour trying to figure out why this silly calorimeter wasn't going on the balance until I figured that out. So just be aware of things like that.
Okay.
The other thing, John, the nice thing about this lab, and Jordan will testify to this, it won't let you go on until you put the exact number in. Okay, Gianna?
hmm
But it has to be the exact number. I was putting in something like 21.10 for one of my weights. When the actual answer was 21.11, it kept on marking me wrong. And I couldn't figure out what I was doing wrong. Okay.
Yeah, I've used the math lab and I remember it not letting you basically put in the data. It'll put like a red box around it if it was wrong.
Exactly. Was it a McGraw-Hill thing?
Yes.
So
I used
that's
it for
based.
my last
So
class.
at least you're used to that. I'm just telling you this up front to be aware of for any frustrations. Okay.
Okay.
All right. Jordan, you've already done the lab. I don't know why you're here.
I don't know. I just joined just in case.
You got through the post lab?
Yeah.
Okay. Did okay with that? Was it hard? I haven't been through it yet.
I didn't think it was too bad. The one thing I like about it is if like you get it wrong, you can try again, and it like you still get the same amount of points for trying again.
See, that's what I don't like about it, but I have to live with it. So good enough. Let's get started on it, and we'll be out of here fairly quickly. Okay. So basically what we're doing here, and this is kind of good in a way because it explains something I didn't really go into that much detail with in the lecture. All right, the calculations really aren't hard. They're not hard. You're using one calculation, which is change of temperature is equal to the constant, which is going to stay the same the whole time, 1.86 centigrade per molality times the molality. That's the only equation you're going to use, except for doing all kinds of complicated subtractions. Okay, what you're going to do is you're going to get the freezing point depression at 3 different concentrations. Then you're going to plot the temperature depression, which is going to be on the y-axis, versus the molality, which is on the x-axis. If you switch them, don't worry, it won't let you go on until you put them right. What happens is you get a straight line, and this is not exactly correct. Let me see, I'm going to end show. The straight line is the Van Hoff factor times the KF. So that's basically where we're going with this. Okay, theory. Freezing point depression is a colligative property. Colligative properties depend on the number of particles, not what the particles are. Our equation, freezing point depression is equal to our constant, which is different for each solvent you use, times the molality. In this case, we're going to be using the KF for water, which is 1.86 centigrade per molal. Now, since we're dealing with particles, you need to understand when you put an ionic salt into water, it breaks up into their individual ions, which means more particles. If I put NaCl in water, that breaks up into Na and Cl, 2 particles. If I put MgCl2 in water, that breaks up into Mg plus 2 and 2 Cl minuses, 3 particles. Al2, parentheses, SO43, that breaks up into 5 particles. Because this equation gets changed then, because when I take the molality, I'm taking the molality of the compound, not the molality of the particles. Because of that fact, I have to adapt the equation so that the equation now becomes the freezing point depression is equal to Kf times the molality times I, where I is the Van't-Hoff factor. The trouble is, when you put a salt into water, I take it, I lost Jordan, so it's just you and me, Jana. Okay? Jana?
Yeah, she said that that she'll see us in lecture.
Good enough. She's already completed the lab, so there really wasn't much point in her being here.
Mm.
Okay, you're understanding what's going on.
Yeah, I'm following along.
The trouble is the Van Hoff factor, what happens when some of these ionic salts get into water, sometimes the water surrounds the whole salt. So you're not exactly making 2 for NaCl, you're not exactly making 3 for MgCl. It's a number that's just a little less than that. So if delta T is equal to my Kf times M and I, if I plot my change in temperature, my temperature depression versus my molality, then I'm going to get a slope, and that slope is going to have the value of Kf times I. So to get the Van Hoff factor, I have to take the slope and divide it by Kf. Make sense, Gianna? All right, now, first thing we're going to do is we're going to set the true freezing point. Simply speaking, we're going to add ice to water, and we're going to determine where the line becomes flat. As the water is cooling, as a function of time, eventually, as it gets closer to the freezing point, it kind of rounds out, and then it goes flat. So basically what we're doing in order to determine where the actual freezing point is we're taking a line. This line should be straight. We're taking it straight down and continuing it on. We're taking the other part of the line after the curve ends, and we are extending that towards the y-axis. Where the 2 lines intersect is actually the freezing point. So we're going to say that our freezing point was about 0.2 degrees centigrade. All right. So now we're going to go on to the actual salt portion of it. We're going to weigh our calorimeter before we add anything, and we're going to add about 50 milliliters of water. We don't need to really worry about that too much. We're going to record the exact quantity, but we're not going to use that in the calculations. What we're going to then do is we're going to put an exact quantity of the salt into the water solution in the calorimeter. After we do that, we're going to take the calorimeter, put it on the balance, and record that mass. We're going to then add ice to that mixture and to record the mixture of the ice, water, salt mixture. We are going to then put this onto a stir plate, put the probe in, and we are going to determine a new freezing point. This time, what happens is the freezing point doesn't stay straight. The reason the line doesn't stay straight is because if we're freezing some of the solvent, doesn't that make the concentration of the solution a little more concentrated? Because we're taking liquid away. So if we're taking liquid away and making it more concentrated, the Kf times m is going to increase. That's why the temperature keeps on decreasing. So what I'm going to do is I'm going to take a line, a straight line down from the descending curve, and I'm going to take a straight line back from the ascending curve, and where this meets is going to be where your freezing point. Now, this is extremely important because it literally took me about 15 minutes in a simulation to figure out what they wanted. What you're going to do is you're going to take your cursor and you're going to take your cursor and put it somewhere close to the line, but somewhere in this direction. And it may take you a little while to figure it out, but that's how you're going to get the freezing point. I was trying all sorts of things, like taking my cursor and trying to draw lines. It didn't work. You're going to need to take your cursor and put it somewhere below the line, just around where the curve is. All right. Next, what we are going to do is we're going to decant the ice and get a mass. All right. Remember, we're plotting temperature depression, which we just measured, versus molality. So in order to get molality, we need the moles of our solute and the kilograms of our solvent. All right. Moles of our solute, easy. We have the mass of our salt. If we know what the empirical formula of the salt is, we just divide the mass by the molecular weight, and that will give us the moles. All right. The kilograms are a bit trickier. We need the mass of water, and it's not a straightforward thing like, oh, well, you just got the calorimeter in water, you just put it on the balance and you subtract out the weight of the calorimeter. It's not that straightforward because as this thing is sitting there, some of the ice has melted and added to the weight of the water. So trust me on this. Vanessa and Gianna, trust me on this. Do this calculation in this fashion. I literally spent about a half an hour trying to get the numbers correct. You're going to take the weight of the calorimeter, ice, and solution. From that, you know the mass of the remaining ice because you are going to decant the water off and measure the calorimeter and ice. You're going to subtract the weight of the calorimeter. That will give you the amount of the remaining ice. So that gets subtracted from the calorimeter, solution, and ice. We know the mass of the calorimeter. Subtract that. We know the mass of the salt. Remember, we only want the mass of the water. So we subtract ice, calorimeter, and salt weights from the calorimeter, solution, and ice. And we get the remaining mass of water in our solution. We then need to take that amount in grams, convert that to kilograms, and we get 0.07302 kilograms. Then the simple molality calculation, take the moles, divide it by the kilograms, we get the molality. So what we are doing here is we are doing 3 trials at 3 different concentrations. The very last thing you're doing in the simulation is you're making a graph of the temperature depression, which is the y-axis, versus the molality, which is the x-axis. You will get a straight line from that. You'll get the straight line will have a slope, and the slope is going to be equal to Kf times the I factor. So to get the I factor, you divide the slope by the Kf, you will get I. Any questions about where we're going in this laboratory?
No, I don't have any questions.
Vanessa? Unmute yourself, Vanessa.
No questions.
Okay, Vanessa, have you done the experiment?
No,
I'm sorry, yes or no?
not yet.
Okay, Vanessa, turn your camera on. Thank you, Vanessa. You're totally dark, but I guess you're complying. All right. So I want to go through and show you what the simulation is like. Click on Colligative Properties report, and that will automatically switch you into the McGraw-Hill section. This is different for me than for you. What will happen for you is this view will pop up. Click on the lab itself first. You begin, read through the material that's there. It's going to help you do the lab. Oh, I'm sorry.
So I just have one question about this laboratory.
Mhm.
So I remember doing it in my other classes, and they basically would want you to do a graph in the simulation, but the very last part of it,
Mhm.
do you want us to translate that to Excel, or do you just want us to screenshot it and that be acceptable?
It'll be in the graph. It'll be in there itself.
Oh, okay.
Literally speaking, you won't have to do anything.
All right.
Okay, ask you some questions. And this, even this is not even this is not easily understood. Okay, if you pick something wrong and you say go to phase 2, it will give you this error message. Okay, so you got to fix these things till it gives you the right answer. Yeah. Yeah. That's not right. How's the cat doing, Gianna? You're muted. I can't hear you.
This is actually my dog. He's
Oh,
being
I'm sorry.
very clingy right now.
Uh, Oh, boom. Yay! It didn't want the freezing point. Yay. Okay, so now you have to do things exactly. It says construct it. You basically, to grab something, you click on it, then move it to where it's supposed to be, click on it again. It will make it. Do everything. If you just try and do, if you just try and do it out of order, it will not work. If you try and grab it, it will not work. You have to do everything before you can, before it will allow you. Yes. Okay. Even that is touchy. Okay. Grab this, put it in there. Now you've got to zoom in, see what the amount is, zoom out, go to lab data. This is okay. This is what happens when I don't pay attention. I got to take this, put it in there. It empties, goes away. Now I'm going to turn on the stir plate. Huh? Did that. Ice. Here. Boom. Turn on the stir plate. Insert this in there. Now, you can sit here for 7 minutes, or you can cheat. Okay? Now, when I was talking to you about the freezing point, that's what I was talking about. You got to put it somewhere below this little curve to get the exact freezing point. Then, okay. I should be able to zoom out of this silly thing. Oh. Part of the thing is that my instructions are, all right, I got to put the lab data in. I have to put the freezing point of the water. All right, zoom out, zoom out. Now I have to remove the probe, place the calorimeter in the waste bin. I'm done. I have to go to the next phase. Again, I have to construct the calorimeter. This time I have to come over here, tear the balance, take the calorimeter over there, go to the data table. Take this, put it back on the balance. Take this, put it in there. Zoom in. Data table. Now, if I put a wrong number in, this little box comes up. I've got to look in. 6 for 7 for the 8. Okay, it didn't like that number. So you got to fudge it a little bit. It liked that one. Are you understanding how picky this thing is?
Yeah, I remember how frustrating it was sometimes to put in points.
Tell me about it. You weren't
It's
with
like
me.
trial and error.
You were not with me at 1 o'clock last night when I was trying to do this. Pick up, I'm sorry. This gets put, wait. Oh, yeah, this goes in here. This goes in there, and this goes. Ah. Okay. Oh. It will not let you go and do something unless you have finished another stage. Okay, you see that? I'm reading my calculator. My calculator says 0.01899. It didn't like 0.018. Didn't like that either. Ah. Okay. All right. Be aware they switched the salts on you. They switched the numbers. Okay. Last night I was working with sodium chloride. Today it's calcium chloride. Okay. Tare balance, or put this in there. Up. Oh, that's right. Are you seeing how picky this silly thing is?
Yes.
Okay. Do you need me to go through the rest of this?
No.
All right. I really did want to illustrate how picky this was. And if you enter in a wrong thing, it won't let you just go ahead straight enter in numbers. You have to do the thing. So if you enter in a wrong number, as you saw with this one, the box will be circled in red. That means that that answer is wrong. Can you go on to the next phase? Yeah. You got to finish every phase in order to get this thing finished. Okay? Questions, ladies and gentlemen?
No, I don't have any.
All right. Let me see if I can get out of here. I don't know whether this will allow me. It's not allowing me to get in there. Basically, what happens, you're going to do all three of those columns like that. Yes, it's going to take a lot of time. Yes, you're going to make a lot of mistakes. But you will get it done. If you make a mistake, the box will be highlighted in red to fix it. At the very end, you will be making a graph of, on the y-axis, temperature depression. Y-axis temperature depression, x-axis molality. You'll get 3 points on that graph. You'll be able to make a straight line, and you'll be able to determine what the slope. It will give you the slope of that line. Then it will ask you the Van Hoff factor. Once you get the slope, you divide that by KF, and you get the Van Hoff factor. Any questions, guys? Anything?
Nope.
Gianna, Vanessa?
No, I don't have any.
No questions.
Okay. Guys, I do think you were fortunate, because I think those people that weren't on here are going to have a lot of questions. And literally speaking, I may not be available for them, because I'm kind of ticked that only 4 of you are here. So if you're out there, ladies and gentlemen, you need to show up to the online, so that if you have questions, I'll be here to answer them. That's all I got, guys. Gianna, Vanessa, you good?
All good.
Okay. Jolene. Jolene?
Yes,
Hi. Class began at 8 o'clock.
yeah, I know.
I've gone through the lecture already.
It's recorded.
At this point, what I'm going to do is I'm going to make a couple comments to you, and I'm going to tell you to go ahead and watch the video, watch Dr. Lou's video. This laboratory is extremely, extremely frustrating. I was up until 2 in the morning last night trying to get through the entire thing.
Yeah, I started it, and then halfway through, I was like, wait a minute, where are we going with this?
Okay, it is frustrating. I'll go through a little bit of it with you, okay?
Okay,
Let's see. I need
First-
to,
like the first page, but then when you get to some of the second page,
Jolene, trust me, I've been there. You
Yeah.
Let me guess, you're getting a red box around the number and you can't figure out why it's. Why it's giving you a red box?
I didn't do that. I went and watched the video where it told me I had E, and then it told me to find out the temperature and then do the calculation. And then it asked what I had.
Sorry, E?
Which lecture are you doing?
I'm doing colligative properties.
Yeah,
That's our next lab.
yeah. Okay, that's what I think I'm doing too.
Okay, there's no E there.
Yeah, I'm doing one online. Never mind. Okay, so you're in. I'm doing a different lab. Okay, go ahead.
Okay, what are you doing?
The one that you print out from the temperature one.
I'm not understanding, Jolene. Jolene, you're in my online lab, right?
Yeah, it's under modules,
Okay,
and
let me,
it's not in my lab or whatever.
it's,
Let me get it out.
okay. All right, I'm in modules right now, Jolene.
Yeah, scroll down.
Oh, no, I'm not. Hold on a second. I got to get into there. There we go. All right. We just
That
did the heat of vaporization.
That's the one. Yeah,
Okay, well, that was the one that I did on
Tuesday.
Tuesday.
Yeah, I know. I missed that class.
Okay, Jolene, what I give the lecture on today was colligative properties.
Gotcha.
Okay, do you have questions on this lab?
No, let's go to colligative properties since it's more difficult.
Basically, all you're doing from the boiling point lab is you're reading the, you're going to the survey and you are reading the boiling point that's in the liquid there.
Yeah, I did
You're-
that.
You're taking that boiling point, going to the chart, to the table.
I did
And you're
that.
identifying the substance. And once you identify the substance, you have the heat of vaporization.
Yeah.
Okay, so you're going to use the Clausius-Clapeyron equation for that, Jolene.
Uh-huh.
And that equation is ln of P1 over P2 is equal to negative heat of vaporization divided by R times, in parentheses, 1 over T1 minus 1 over T2.
Yeah.
Okay? By boiling the liquid, by seeing the liquid at the boiling point, you know that the pressure is 760 at that point. So you substitute 760 for torr for the P1 and 1 over the boiling point plus 273. The question for that part asks you, what is the pressure at some other temperature? So you
Yeah,
got to,
plug and chug.
so
Yeah.
you're good with that one, right?
Yeah. Yeah.
All right. The second one you have to do, you're given a table and you have a table of pressures, water vapor pressure and temperature, right?
Yes.
All of the pressures, you have to hit the ln, plug in the number, record that for the ln of the pressure.
Yep.
For all the temperatures, you have to take 1 divided by that temperature turned into Kelvin. So you have 2 new columns, ln of P versus 1 over T.
And then put it in Excel and then get the slope, do all that. I can do that.
Okay, so you're good with that?
Yep.
All right. Colligative properties.
Yes.
Okay. Basically, and I will, equations are not hard. These really aren't that hard. Basically, what we're doing is we are taking our basic equation is the freezing point is equal to a constant based on the solvent times the molality. Now,
Okay.
colligative properties are based on particles. So if I put a salt into a water, the salt breaks up into its ions. So where I had sodium chloride before, I now have 2 particles. Where I have mag chloride, I now have 3 particles. So the molality of the sodium chloride has to be multiplied by a number to take that into account.
Okay.
Trouble is, those numbers aren't whole numbers. Sometimes what happens is the entire salt molecule gets surrounded by water. And so it doesn't add another particle for that molecule. Does that make sense, Jolene?
Yeah.
So the Van Hoff factor for sodium chloride is a little less than 2. So what we're doing now is we are going to plot our freezing point depressions versus molality. We're going to plot that. And since the freezing point depression is equal to this constant times I times the molality, if I do that plot, my slope is going to be equal to my Kf constant times my Van Hoff factor. So I divide the slope by Kf, I'm going to get the Van Hoff factor. All making sense, Jolene?
Mhm.
Okay, now, when we're doing these graphs, when you do them in the program, it's going to tell you to move the cursor to where the freezing point is. What happens is the freezing point decreases with time. Then there's this little kind of like rounding, and then it's going to be flat for pure substances. What they want you to do is they want you to move the cursor somewhat a little bit underneath this curve and click on it.
Okay.
Then the freezing point will be displayed and you can enter it into the data table. You're going to go through a series of weights. You're going to weigh the calorimeter. You're going to weigh the salt. You're going to add the salt to the water and you're going to record the mass of the calorimeter, water, and salt.
Okay.
You're going to add ice to it, record that mass.
Got it.
Then you are going to put the probe into the ice solution and record the temperature.
Okay.
The temperature is going to be a little bit different because the line where it was before with the pure substance, it stayed straight. Now it is slanting off because literally what's happening, Jolene, is the liquid is freezing. As the liquid freezes, the liquid that's left becomes more and more concentrated.
Okay.
So again, you're going to take it a little bit below the curve, click on it, get the new freezing point. Then you're going to decant the ice from the calorimeter. And you're going to take the calorimeter and remaining ice, put that on the balance and get the weight of that. To get the molality, you need 2 things. You need the moles of the solute and the kilograms of the solvent. Solute, you weighed, just divide that by the molar mass, you're going to get the moles. Kilograms is a bit trickier. You're going to have the weight of the calorimeter, solution, and ice. You know what the weight of the remaining ice is. You're going to take the calorimeter and remaining ice and subtract the mass of the calorimeter from that. That will give you the ice that was in, that remained. You know the mass of the calorimeter, you subtract that. You know the mass of the salt, you subtract that. You subtract all these things from the mass of the calorimeter, ice, and solution. Trust me, Jolene, I was up at 1 o'clock last night doing this calculation and I was entering the number and it was keep on giving me an error message. If you do it in this fashion, it will work.
And then we do the new ice over the old ice times 100. I mean, divide it, you know, the new ice divided by the old ice times 100 to get your.
You're subtracting all these things.
No, I understand. I understand. And then after you get your new ice, your value of your ice before this, the ice before you started and the ice after you started, then you're going to go through and do what?
Okay. I'm not understanding what you're saying. I'm trying to tell you, this is the way, the information you need, Jolene.
Yeah, we're getting the values of the ice before.
You're
We
getting the
did,
value of the calorimeter, ice, and solution.
and we're subtracting the calorimeter from the solution, from the ice from the calorimeter solution to get the original weight of the ice.
Now you're subtracting. You don't need the weight of the original ice. You don't need that.
Okay.
Because Jolene, some of that ice has melted and added mass to the water. That's why
Okay.
you don't need the weight of the original ice.
Okay, calorimeter minus solution minus, okay,
So you take, all right, first thing, you subtract the calorimeter from the calorimeter, ice, and solution. This gives you the weight of the ice and solution.
got it.
All right. You have decanted the water away. At the very end, you're decanting the water away. So you're left with ice and calorimeter. You subtract the mass of the calorimeter from that. That gives you the mass of the remaining ice. All
Got
the
it.
other ice was converted to water.
Got it.
So you subtract the mass of the remaining ice from the calorimeter, ice, and solution.
Mhm.
That will give you the mass of the solution. Subtract the mass of the salt from that. That gives you the mass of the water. Simply speaking, after that, you take the moles of the solute divided by the kilograms of the solvent. That gives you the molality. You're doing 3 trials, 3 different molalities, 3 different freezing point depressions. At the
Okay.
end, you'll get a straight line graph. It will lead you through doing the graph in the program.
Yeah,
You'll get a straight line graph, and don't do the mistake I made. I just said that the slope was the I factor. That's not true. You have to take the slope and divide it by KF, which for water is 1.86. That will give you the I factor. Good
Okay.
enough?
perfect. I wrote it down and I'll watch the video. I'm sorry I'm late. I woke up, but then I fell
No,
asleep.
things happen. Do you want me to go through? It's up to you. Do you want me to go through the simulation? Jolene, it is very, very frustrating.
Can you give me your number? Because I have to drop a baby off at daycare. Can I call you back? It's 727.
202-7275, but I'm not going to be here.
Okay.
Jolene, from literally 10:30 until, I'm sorry, 10:15 till 12:20, I'm teaching a lecture.
Oh,
After
okay.
12:20, I am driving over to Hillsborough.
Okay.
Okay. And I teach a lab there this afternoon. So I'm not going to be back in my house until about 5 o'clock, and I'm going out to dinner tonight.
Okay.
So
I'm in
today is not a good day. I know you have to go out to daycare.
It's okay. I can skip her in daycare. Just, I can start now if you want.
No, that's up to you, Jolene.
Yeah, I think it's important if it's tricky.
Okay. I'm going to stop share. Screen is going to go on to here. To get into this Colligative Properties report. And what's going to happen is it will take you automatically to the McGraw-Hill. I don't know why maybe I hit assignment. I don't know what I did. This should take you directly, the properties report should take you to the McGraw-Hill. Oh, it's already open. My screen's a little bit different from yours. This should be what yours looks like right now. Okay. Simulation part. Read through this stuff. You're going to need to know this stuff in order to do the simulation. So it's going to ask you a couple questions. These questions really aren't easy. And it's another thing that gets frustrating. Okay. Now we're in the simulation, Jolene. You got to read everything that's there. Okay. What I was doing forever.
Do you know you
But-
can go back and forth?
Yes,
Okay.
I do know that. All you have to do is hit the reset.
No, you can go up to the top bar where it says lab simulation and you can go back to introduction as you're working through the lab. So you can
Where?
reread that you might have missed.
Oh, you mean there?
Yeah, you can
Okay.
hit that, go back and forth.
Yeah,
So you-
yeah, I did know that.
Okay.
Okay, now the thing is, Jolene, it took me the longest time to figure this out. Okay? I
I'm
went
not-
through, I put this,
So a question I have to answer and then I can get to that point.
what's that, Jolene?
You're in a different phase than I'm on. I'm not on your phase yet. Give me 1 second.
I'd rather you look through and see what I'm doing on the screen rather than
Gotcha.
try and work through it with me, okay?
Got you.
Okay, so I've got the cups in there. What I did was I just went, okay, place the assembled calorimeter on the stir plate, and I'm trying to grab it. And it's giving me this error message. I can't grab it and put it on here. Finally, about 15 minutes later, I realized, oh, I got to put the stir bar in here. And I got to put the cork on here. Now I can grab it and put it on the stir bar. You got to read all the instructions. If you don't do what they tell you, it won't let you proceed.
Yeah.
Okay. Now you got to take the graduated cylinder, click on it. You now have your graduated cylinder filled with water. Why they're making you do this, I don't know, because you don't need this measurement. Then you zoom in. Okay, it's telling me 50.0 degrees or 50.0 milliliters. Zoom out, go to the lab table. If you enter in, damn it. Okay, now I know. Jolene, I've been at this for about 4 hours. Okay.
If you enter in 50
If you
mil,
enter the wrong thing, it won't let you go because it was
Yeah.
telling me to pour the water into the calorimeter. Then add the beaker of ice to this. Throw that away. Turn on the stir plate. Insert the calorimeter. Now, you can cheat, Jolene. I don't care that are you seeing the red line start?
yeah.
You want to wait? Do you want to wait 7 minutes for this to end?
No.
Hit the one thing. It speeds it up by a minute at a time. All right. Now to get the freezing point,
Just below the line.
you just basically want to put it like right about there. That makes the two intersecting lines and you read the freezing point. Now, again, it's not going to let you go to the next step until you put the information into the data table. You notice the zoom out didn't appear until I put that information in there.
That's right.
So now you take the probe out, you take this, throw it away. Go on to the next phase. Next phase, again, calorimeter, boom. You're going to get used to doing this.
Yeah.
Okay, now you have to tear the balance, take this over, put it on the balance, record the weight. If I record something even that close, it's going to put a red box around it. So it wants what it wants. If you don't put in the right amount of significant figures, you're going to get a red box and it won't, and it'll allow you to go forward but it will tell you that you've made an error, okay? Now you put this back here, put this in there again. Read that as 47.1. Lab table. Oh, we're putting glucose on it this time. Okay, then it tells you to put this, nope. Oh. Weigh balance, tare, scoop. Boom. Lab data. I'm sorry to go through this like this with you, but oh. Do you see how it will not allow you to go on? And it gets to be extremely frustrating because it gets to be extremely frustrating because you're trying to fit, you don't, that doesn't tell you why you got it wrong. It just
Where'd you
tells you
get
you're
that
wrong.
From 0.019.
What's that?
Where'd you get 0.019
It
from?
asks for the moles.
Oh, okay.
I knew that the molecular mass was 180, so I divided this 1.97 by
couldn't read.
180.
Yeah, I can't read the screen that well.
I'm sorry. This
Wait,
is
let me turn sideways. Never mind. I can make my phone bigger. Got it.
okay. Hmm.
Doesn't
Wonder if I
like-
got the, doesn't like the 0.10. I know why.
Throw another 0 on there.
No, it should have been a negative.
Oh, yeah.
So basically, what I would have to do is I would have to, at this point, hit this. In order to change that number, I would have to then go to reset.
Are you kidding me?
No, I'm not kidding you.
Oh,
Current
my
phase,
God.
make sure you do not hit edit. At that point, make sure that you do not hit enter entire laboratory simulation. And then what you have to do is you have to go through that entire process again.
Okay.
I'm sorry. This is what's
That's
given
what
to
it
me.
is. Yeah.
What I wanted to do is I wanted to show you some of the frustration that's involved in it. And
That's one of them.
yeah, and I think that this was, oh, cup. Okay. Oh, this isn't even where I wanted to go. Sorry.
You're fine. I appreciate the help.
Okay. Ah, crap. Oh, that's just why. Again. Okay. Again, I don't know why this isn't working at this point. I don't know why. I'm sorry. God
This is
bless
very
you.
frustrating.
God bless you. The nice thing about it, Jolene, is that at the very end, if you do it correctly, you know you get 100%.
Yeah,
Bad thing is the frustration that's involved in things like this.
yeah.
Good luck with it.
Thank you. I will,
If you have any
I-
questions, give me a
I'll
call.
call later. Yeah, I'm gonna work on it later on today.
I should be
It's
available
due
on
the
Friday.
6th, right?
What's that?
This one's due on the 6th.
This is due on Sunday. Sunday
But
at midnight.
But the heat vaporization one is due today.
Nope, heat of vaporization is also due Sunday.
Okay, got you.
Whatever we do that week is due Sunday at midnight.
All right, that makes sense.
So next week we are going to be doing, God help us, we are going to be doing chemical kinetics on Tuesday and determination of an equilibrium constant on Thursday. Those
Okay.
will be due on the 13th.
Okay, that makes
Right.
sense.
So
I appreciate you. Thank you so much.
no problem, Jolene. I'm here to help. If you need help, I am available tomorrow. Saturday, I probably won't be. I'll be around on Sunday.
Sounds good. Thank you.
All right, you take care.
All right, bye-bye.
Bye.
All right, Nadia, let's get ready for school. We're going to eat your food. We're going to school today. There's no mom about it. We're going to school today.
Okay, Jolene, I'm getting you out of here.
Yeah, close up.